Hello, this is Kyle Davidson, and today I'm going to be doing an introduction to MATLAB for engineers with a focus on some of the signal processing aspects we can use for it. But really, these skills are applicable to any basic engineering use of MATLAB. And by the end of this, you should be able to do three things. And the first is create and write short programs in MATLAB using M files. The second one is perform vector math, which is basically how MATLAB efficiently implements a lot of the mathematical calculations instead of using loops. And finally, we're going to discuss how to plot data, visualize it both in the time and the frequency domain. So we're going to start with MATLAB open right in front of you. And we've got a few things going on in front of us. The first is the command window, which is this right here. Over on the right, we have our workspace. This is where the variables are held. In the center, we've got the editor where we can type our M files and modify any variables if we open them. And over on the left, we have the current folder that MATLAB's active in, because these M files we'll create that are our programs are stored in a specific file on the hard drive, like everything else. But MATLAB has to know kind of where to look for them. So I'm going to type in CLC first to clear the command window. And we're going to start doing some simple help files information, because really before we want to do anything else, if we want to, for example, take sine of 2 times pi, we want to know what that, which is approximately 0. That's actually the lowest. What you see there is the F's value, the lowest MATLAB can calculate, basically. We need to find out what that sine function is doing. So to do that, we type help sin. Now if we want to find out what sin degree one of the associated files does, we can just click on that and it pops up. And in this case, it turns out sin d is the MATLAB function for sine in degrees, because the basic sine function is in radians. For more complicated help, though, we type in doc and the name of the function we're interested in. And plot is a good example. So we see it pop up there. Here's the basic information at the top for all the plot parameters. If we go down a little, though, we can start seeing some examples. And there is a sinusoid that's been plotted using the plot function. And then if we want to change the line styles, all the various pieces of information. And this is a good function to refer to in the help, because it has a lot of parameters, and they're certainly hard to remember even after all my years of using it. Now that we know how to access help, the next step is to create an M file, because while we can type in, A equals 3, B equals 2, and C equals A plus B, that gets repetitive and not terribly useful for anything longer than a couple lines. So we go up here, we have the plus sign. I'm going to close this down and use this MATLAB file I already created. And we'll save it to the hard drive. It's already been saved, but we'll do it again. Now, once we're in an M file, MATLAB's an interpreted language, which means it's not compiled. We don't take the lines of code, convert it to a binary format, and then the computer executes it from there. It's done literally line by line, like Python. So if we want to comment it, well, we use the percent sign. But if we put 2% signs, we create what's called a section. And we can actually create lines of code and execute them separately like this by separating the sections. So I can run this entire M file now. And we'll see over on the right we have A is equal to 3, B is equal to 2, and C is equal to 5 because we've added them together. But if I want to clear all the variables by typing clear all, I can actually run this by section. So I click the run section button, the first part executes, the second part executes, and now we've got our two variables stored over on the right. Handy when we're debugging. From here, we can actually publish this, and this gets handier in larger programs But when I click publish, it actually takes my information and turns it into essentially a document and help file on everything I had. So the sections become section cap links here, and the text which was commented just below the section ends up appearing as normal text there. The MATLAB code and any figures. And to give you an example, we have a file I've created here for some work I've been doing on Wiener-Field distributions, and there we actually have all the code. It's typed up nicely using essentially LaTeX formatting to produce the math, and then the figures actually appear right in the line, which is a very useful function. Now, I've got a basic M file. It executes code. It does stuff. Where do I go from here? Well, there's a few numbers you should know about. And those numbers in MATLAB that are important tend to be pi, exp, which is the natural number, and the imaginary numbers. And we can use both I and j inside MATLAB. And there I've added I and j, and we get 2i, because they both represent the imaginary number to keep both the electrical engineers and physicists happy using their preferred formatting. Now, what we need to do is start dealing with MATLAB in what it was designed to use, arrays or matrices, because MATLAB actually stands for Matrix Laboratory. And we can do this in a few formats. To create a row vector, I simply type in 1, 2, 3, 4, separated by spaces, and I get a nice row vector. If I want to use B, 1, 2, 3, 4, separating each of the numbers by a comma, I get the same effect. If I change it to a semicolon, that indicates it's a new row, and we get B looking like a column vector. Now to change that around, I simply put an apostrophe after it, and that'll do the transpose. And now B is gone from a column vector to a row vector. So that's fine, and if I want to access any one of the individual elements, I can type A2. That gives me the second element of the array. But that's not where sort of the power of MATLAB comes from. We need to start doing multi-dimensional stuff. And we're only going to do two-dimensional today, but if I say, for example, A equals 1, 2, 3, 4, 1 space 2, then the semicolon indicating a new row, and then 3 and 4, I have a 2 by 2 array. And we'll do B equal to, let's say, 1, 1, 2, 2. I've got my A and B matrices, both are 2 by 2, and I can multiply those two matrices together. Fantastic. So there I've got two arrays multiplied together using matrix multiplication. This is not an element by element multiplication. And that's where MATLAB can get a little tricky. So I can do all the normal math functions inside MATLAB. So I can do multiplication with the asterisk, division, an exponential, addition, subtraction, and so on. But more commonly, what you'll see in MATLAB is you want to do an element by element operation, and there we simply put a period in front of whatever function we're doing. So in this case, I've said A period exponential B, little hat, and we get the A matrix to the power of whatever the element, its respective element in the B matrix is. So what we're really doing is A1 to the power of B1. A 2, 1 to the power of B 2, 1. And we could implement the same functionality with a for loop, for example, going through the indices for each one of the matrix elements and then multiplying them respectively. But MATLAB simply lets me go, A period times B much more efficiently. And this works as well for 2 and 3D arrays and other functions. Now MATLAB obviously has all sort of the standard math functions available. For example, the absolute value of 1 plus j, square root of 2, the angle of 1 plus j, we'll return the angle in radians. We can do the logarithm in base 10 using log 10. We can do the logarithm in base e, the natural number, using just log. We can round, and you can look up those various functions yourself, really as you require them. So what we're going to do now is take our M file, and we're actually going to name it, give it a section title of create sinusoid, and then we're going to explain that it creates a sinusoid of 1 kilohertz and plots the results in the frequency and time domain. And then we'll create another section, which we'll call plot sinusoid. And that's what we're going to do with these two different parts of our M file now. We're going to create two arrays which represent a sine and a cosine at 1 kilohertz, and then we're going to plot the results in the frequency and the time domain. So to do that, we first need a center frequency. We'll just call it f, and it's going to equal 1e3, or 1 times 10 to the power of 3 hertz. We are going to use a sample time, f of f, sampling frequency of 100 times the frequency of the wave. And we're going to run the simulation using a variable called t-stop or time stop for a couple periods of the wave. And the wave is at 1e3. Its period is 1 over f, and we'll do 2 of those, so we'll simply multiply that by 2. And we can run this, and you'll see the variables appear over on the right. The next step is we need to create a time matrix, and this is done using a fairly simple process. We start at 0, and we want to increase it by some increment to a final value. An increment in this case is going to be 1 over the sampling frequency, or the sampling period. And the final value is going to be our t-stop. By the way, MATLAB is case sensitive. So if we run this now, you see over on the right, we have an array of 1 times 201 values. And if we look at t from, let's say, 1 to 10, 1:10, we see the first 10 values, and you can see it's incrementing by the sampling period from one step to the next, starting at 0. All right. So we have all the time values we're going to create our sinusoid for. Now we just need to create the sinusoid, and that's pretty simple. Sine of 2 times pi times f times t, just like we do with the math. And then we can run it, and we end up with, again, a variable over here, x, being 1 by 201 double floating precision floating point values. And that doesn't do us a whole lot of good, though, right? We can look at those values in memory, and that's fine, but we want to see it plotted now. And we'll do that by creating a figure, figure 1, and plotting t, our x and our y values. So x is going to be t, y is going to be our x. And if we run this, we get our nice plot. We can see it going between 0 and 1, minus 1 and 1, and we can see the 2 periods. But we need to tweak a few things here because I'm not quite happy with how it's being visualized. First of all, we can see all the values down there from 0 to 2, but they're multiplied by 10 to the minus 3. So I'm going to get rid of the convert it. Actually, we'll convert it to microseconds, and by multiplying by 1 to the power of 6. I'll give it an X label. And all it's asking for there is to enter a string representing the X values. And we can call it time. And we can use microseconds. And we can run it again, and now we see at the bottom, time in microseconds. Now, MATLAB does have one little trick here that is worth mentioning. It interprets LaTeX commands in text when displaying them for plots. If you're not familiar with LaTeX, it's a typesetting software used for academic purposes mostly, especially since it's really good at the math. And if I want to display mu, I simply type \mu for the S. And now we can see the Greek letter mu in front of the S, indicating microseconds. So we'll flesh out the rest of this plot now. The y-axis will be labeled as amplitude using y-label and have units of voltage. And we'll give it a title of sinusoids. And I just need to put the apostrophes on either side. If we run it now, we're good. We can see the amplitude over here, title of sinusoids, and if I go to publish now and publish this, we can see the results appearing in documentation just like we want them to, the titles, and the plot actually included right here, which we could then just save as a figure. So that's fine, but we want to add another plot. We want to add the cosine. So to do that, I'm simply going to copy and paste X again, change its name to Y, and I'll change it from a sine to a cos. And if I use the plot command, copying and pasting it down here, and plot Y instead, I can run the file again. We get the same plot appearing, but notice that everything's disappeared at this point. The original plot isn't there, we just have the new one, and all the labels are gone as well. So how can we fix that if we want to see both at the same time? Well, the answer is pretty straightforward. We simply type hold on, and afterwards we'll take our hold off. And hold on indicates that you have a plot, add the additional plots to it instead of overwriting what was already there. So we've run it again. We can see the sine and the cosine there. We have all our original labeling, and that's exactly what we wanted to see. And the last thing we'll want to do there is actually add a legend, because we have two plots on there. We'll call it sine and cos, and we've simply used, we've got two plots, so we need two things separated by a comma, a sine and a cosine, both in the apostrophes like that. And if we run it, now we can see sine and cos. If I want to do one more thing though that's worth mentioning, it's that after the second plot, just to distinguish them a little, I may want to change the plot to a dashed line, which I've done there by adding a double dash inside quotations. If I run it, now we can see the red line is dashed. And if I want to change the color, I can add, for example, a G beforehand. Run it again, now we can see the dashed line is green. There is all kinds of options here for how we plot information, and we can change that as required. If you really want to look up the details, again, go into the documentation on help. So the last thing we want to do today is add the frequency domain information, but we're going to do it using a command called subplot, so we can see both at the same time in the same figure. And I'll actually write that before I explain what's going on. So we type subplot 2, 1, 1. And then I'll do another one down here, subplot 2, 1, 2. So I've typed a command subplot, and it's sort of like an array of 2 dimensions. Says the number of rows and the number of columns of plots I want on my figure. In this case, 2 rows, 1 column, and the last number here indicates which plot is active. So the first one's active here, and down here at the bottom, the second one's active. So if I type, well, Actually, we'll do the frequency domain information first. So I want to create a frequency domain version of the sinusoid. So XF, we'll call that variable. And it's simply going to be FFT, the fast Fourier transform, of X. Now, that's fine on its own, but fast Fourier transform actually lets you pick out the number of points. And we'll call that NFFT. NFFT is going to be 256 points. Actually, sorry, it should be a maximum of 201 in length, so we'll say it's 128. That's going to give us the fast Fourier transform, FFT of X, and the number of points is should be capped at the length of your array. Often you want to drastically lower it for computational efficiency, which we can see happening right there. So the next step is to actually plot this, but we need to plot it against something. So we're going to use another command called linspace, and frequency is going to be equal, is the variable we're going to use to create this array of values from the sampling frequency, negative the sampling frequency divided by 2, to the sampling frequency divided by 2, that is our Nyquist frequencies. And we want to create an array between those two values of the same length as the, I just noticed an error there, that should be n, of the matrix I'm looking at. So NFFT, if we run it quickly, our frequency domain value is a length of 128. So X of F is 128 values. So that's fine. And we'll say then linspace minus F of S divided by 2. F of S divided by 2. So the values we're going to, and NFFT. So what we see there is it's telling MATLAB to create a variable frequency that's a vector from linearly spaced from minus the sampling frequency divided by 2 to the sampling frequency divided by 2, and use NFFT points, which is the length of our Fourier transform values. And now if we look over on the right, we can see freq has 128 values, the same as XF. So we can plot this now. Plot freq, comma, XF. Before we do that, though, we need to do something important. And since this is a complex number, we want to plot only the absolute value. And I'm going to run this, but in a second you're going to see there's an issue. And the issue is fairly obvious right off the start. We can see our spikes should be at 1 kilohertz, but they're not. And I'll multiply, so divide this by 1e3. Add a label, X label, frequency, in kilohertz. Run it again, and now we can see that we have some spikes, but they're up at essentially a minus like 49 kilohertz and plus 49 kilohertz, and that's not where the information should be. It should be here at 1 and minus 1 kilohertz. So what's wrong? Well, what's wrong is how MATLAB calculates the FFT, and it's done for computational efficiency. It essentially spits out the values flipped around, and we need to flip them around to correct for that by using the command FFT shift. So we wrap that around our FFT, run it again, and now we can see two spikes directly at 1 kilohertz and minus 1 kilohertz, which is exactly what we were hoping to visualize. So that was an introduction to MATLAB. The last thing I will mention before I finish here is if you don't have access to MATLAB, for example, it is fairly expensive, and hopefully if you're a university student you can access it through there, but if you want to work from home, you're either stuck shelling out a few $1,000s if you're buying the commercial version, or about $50 for a student version. Well, as an alternative, you can go and download a program called GNU Octave. And you can find this on the internet. It's available for both for Linux and Windows, and it's simply an open source version of MATLAB. The code is identical. It should execute both with MATLAB and Octave perfectly. The only difference is the packages that you have installed. So I do recommend being careful that when you're calling certain functions, the way MATLAB works is you buy them as a group, like the signal processing package or the communications package. Though that provides a number of functions available to you, and then they may or may not be available identically across both Octave and MATLAB. Though the vast majority of the ones you're familiar with from MATLAB you'll see in Octave as well. So I hope you found that helpful. That was an introduction to MATLAB, and if you have any questions, please feel free to leave them in the comments.